Okay, so in the previous two parts of this lecture, we saw how to calculate a Riemann sum to find the area under a curve. Now I'm gonna talk a little bit more general about it, of how you actually get the width, how you get the height in more general terms. First of all, to get the height or the partitions, let's say somebody came up to you and told you, okay, I want you to find the area on this curve using 15 partitions. Well, now you have to figure out what the width will be, because the width is not given to you. In the previous example, the width was given to me. So if the width is not given to you, then you definitely need to know the following. This is a definition about the regular partitions, and there's a simple formula that you just need to know. I'm gonna write the formal definition and just give you the piece that you really need to know. So suppose you have a closed interval AB. So there's a closed interval containing n subintervals. So just basically a bunch of mini intervals within it. So let's say those subintervals are x0 to x1, x1 to x2, x2 to x3, all the way up to xn minus 1 to xn. Right? These are all of equal length. And their length is given by delta x is equal to b minus a over n, with a equal to x0, b equal to xn, and obviously n is not equal to 0 because we cannot have division by 0. Anyway, the endpoints x0, x1, x2, all the way to xn, well, x minus 1 and then xn, of the subintervals, they're called grid points, and they create a regular partition. Of the interval AB. Now, playing Justin Bieber, Baby, official music video featuring Ludacris and YouTube. Well, that's not what I want. Definitely not what I want. And I'm not cutting that out, but my phone began to play Baby by Justin Bieber. And that's a shame. Yeah, I'm not cutting that out. Sorry about that. In any case, they create a partition of the closed interval AB, and in general, this is the important piece, in general, the kth or ith grid point is xk is equal to a plus k times delta x for 0, 1, 2, all the way to n. Now the important piece here is this delta x. Delta x is the width of the partition, is given by b minus a over n. So if somebody comes up to you and they tell you, okay, say you have f of x equal to let's say negative x squared plus 5 again, the one that we had, and you're looking at the interval, let's say close interval 3 to 10, right? And somebody tells you, I want 50 partitions instead of 5 like we had before, or instead of 100, let's say they want 50. Well, to find the Riemann sum and the area under this curve, you first need to compute delta x, which is b minus a. In this business, b is the biggest value, a is the smallest value, so this is going to be 10 minus 3 divided by n, which is 50. So let me actually rewrite that. So this is b minus a over n, which is 10 minus 3 over 50, which is 7 over 50. Okay, so the width of each rectangle is 7 over 50. Now notice that the xkth term is a plus k times delta x. This is very useful because the xkth term is what's going to give us the height. So here we have our function is x squared plus 5, but the xkth term is a plus k delta x. Well, now we know what k is. K is just k, but delta x is 7 over 50, and a we know is 3. So we have that xk is equal to 3 plus k times 7 over 50. Okay, so that's the xkth term. So when we find the Riemann sum for this area, we're looking at the area at the sum from k equals 1 to 50, because n is 50, of f of xk times delta x, where delta x is the height and f of xk is the width. But in reality, we know that this is simply equal to f of 3 plus 7 over 50k times, where obviously k is 1, 2, 3, so let me just actually write it like that. That's 1 times delta x, which is 7 over 50, right, plus f of 3 plus 7 over k times 2 times 7 over 50, and so on. So what you really have when you simplify this, what you really have is the following. You have 7 over 50, the width, times f of 3 plus 7 over 50 plus f of 3 plus 2 times 7 is 14 over 50 plus f of 3 plus 21 over 50 plus all the way up to f of 3 plus 50 times 7 over 50 times 7 over 50, which is simply will be 3 plus 7, because the 50s will cancel out, and then you'll just get 3 plus 7, which is 10, which makes sense because the last point, because we're doing the right endpoint for this sum, we're doing the right endpoint, is 10, because that's the last endpoint right here. And then you'll multiply all of them times 7 over 50. So this is the height of all of the rectangles times the width of all of them, and that will give us the Riemann sum. So this is basically how you solve a Riemann sum, whether it's a left Riemann sum or a right Riemann sum. In fact, I'm going to give you that definition in a second, but this is how you do it. You first begin by finding out the width of the rectangles. Then you figure out what the height of the general height of the rectangles is by finding out what the right endpoints are, or left endpoints, or midpoints are. You know, you do have choices between them. You could choose middle, left, or right, or the upper or the lower. And then you just put it together as a sum, much like I did here. I put it together as a sum of the height times the width. If there's anything that you take away from this Riemann sum section, a Riemann sum is just the height times the width, all added together. Okay? This width is given by your delta x. This height is given by f of your xk. All right, so let me actually give you some definitions. All right, so all right, so definition. And hopefully Justin Bieber don't sing again. Riemann sum. Right, so suppose f is defined on a closed interval AB, which is divided into n subintervals of equal length delta x, if xk is any point in the kth subinterval xk minus 1 to xk for k equals 1, 2, 3, all the way to n, then f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus all the way to f of xn times delta x is called a Riemann sum. For f on the interval AB. Now, much like I was mentioning in the maple piece of this lecture, this sum is called a left Riemann sum if xk is the left endpoint of xk minus 1 and xk. A right Riemann sum, so it's called a left Riemann sum, it's called a right Riemann sum if xk is the right endpoint of xk minus 1 and xk, and it's called a midpoint Riemann sum if xk is the midpoint of xk minus 1 and xk. Again, for this is all for k equals 1 to all the way to n. So that is the definition of a Riemann sum. Now we're gonna be working with Riemann sums throughout, but in sigma notation, I just want to write to you how you write this in Riemann notation. So in Riemann notation, in sigma notation, in sigma notation, then the following is true. So if f is defined on a closed interval AB, which again is divided into n subintervals of equal length delta x, then if xk is a point in the case of interval xk minus 1 to xk, then for k equals 1 to all the way to n, then the Riemann sum which is the important piece. The Riemann sum for that function f on the interval AB is the following sum. It's the sum from k equals 1 to n of f of xk times delta x. And then we have three cases that arise. So the left Riemann sum, as we had before, is going to be given by the following. So the left Riemann sum is given by the sum of k equals 1 to n of f of xk times delta x if xk is equal to a plus k minus 1 delta x. Remember, a is just the value of the interval. So, and this is much like we had in the earlier piece of this lecture. This k minus 1 or I minus 1, it doesn't matter what the indexing variable is. It's just going to be that variable minus 1. It's going to give you the left endpoint. The right endpoint will give us the right Riemann sum, which is given by, it's the simplest one, the sum for k equals, it's supposed to be a 1, not n, 1 to n of f of xk times delta x if xk is equal to a plus k delta x. And finally, the midpoint Riemann sum is given by the sum of k equals to 1 from 1 to n of f of xk times delta x if xk is equal to a plus k minus 1/2 times delta x. Okay? Now again, the partitions is given by b minus a over n. So this is what delta x is equal to. Okay? That's what delta x is equal to. You take the endpoints, you divide it by the number of partitions that you're looking to solve for. Let me see if we could do an example. Let's see. Okay, so let's do a right Riemann sum for the following. So, example. Let's let R be the region bounded by the graph of f of x is equal to 3 times square root of x, and the x-axis between x equals 4 and x equals 16. And what we will do is we will approximate the right, left, and midpoint Riemann sums using 6 partitions. Okay? So that's what we're going to do. So the area that we're interested in looking into is 3 times square root of x for this partition. So the square root of x function looks like this. The 3 just extends it. And we're looking between x equals 4 and x equals 16. So the area that we're looking to partition is this region R. That's what the region is. And because we're using 6 partitions, we are using 1, 2, 3, 4. So we have Um, Actually, this is not even the best way to do it. The best way to do this is, so you have 2, and that's 3, that's 4, and that should be 5, and then it should be 6, right? 1, 2, 3, 4, 5, and 6. Yep. So you just cut them in half. So you have 6 partitions here. And the question is, first of all, what is the width? So what is the width? What is the endpoint? And then what is the Riemann sum? So we will begin by using the right Riemann sum. So the right Riemann sum, as we have from above, by definition, is the sum of k equals 1 to n of f of xk times delta x for xk equal to a plus k times delta x. Now, to get the delta x, remember delta x is equal to b minus a over n. But we know what b minus a is because we're working on the interval 4 to 16, and we know that we want 6 partitions. So we know that n is 6, and we know that a is equal to 4, and b is equal to 16. So we have that delta x is equal to 16 minus 4 divided by 6. 16 minus 4 is 12. 12 divided by 6 is 2. So we're looking at partitions that have width of length 2. Now, xk, since now we have the value of delta x and we have the value for a, by definition, xk is equal to 4 plus 2k. Why? Because a is 4 and k and delta x is 2. So it's 4 plus 2k. And guess what? We're almost done. Because now we know that the right Riemann sum is given by the sum from I equals, now remember where we begin, we just have to be careful with the index. Well, our index is going to go from 1 to 6 because we're using 6 partitions. So it's going to go from 1 and n is equal to 6. So it's 1 to 6. And this is going to be equal to f of xk times delta x. So this is equal to I equals 1 to 6. Now f of xk is the same thing as f of 4 plus 2k times the height. Remember the height is 2. So really what we have here is we have the sum, the following sum. We have the sum of, I'm going to put the width on the outside, and we have f of 4 plus 2 times 1 plus f of 4 plus 2 times 2 plus f of 4 plus 2 times 3 plus f of 4 plus 2 times 4 plus f of 4 plus 2 times 5 plus f of 4 plus 2 times 6. Okay, so that's what our sum is equal to. Now, keep in mind that we are dealing with the following. We are dealing with we're dealing with the following sum. So this is 4 plus 2, that's 6. 4 plus 4 is 8, and so on. So let's see what we get. Let's see what we get. So we have 2 times f of 6 plus f of 8 plus f of 6, 10 plus f of 2 times 4 is 8, plus 4 is 12, plus f of 10, so 14, plus f of 2 times 6 is 12, and 16. I'm missing one value here. Let's see. No, I'm not. Never mind, I'm not. All right. So let's see, 1, 2, 3, 4, 5, and 6. Yeah, I'm not. All right, so let's see what we have. So remember f was given to us originally to be 3 times square root of x. So we have f of 6, well, that's 3 times square root of x, in this case is 6, plus 3 times square root of 8, plus 3 times square root of 10, plus 3 times square root of 12, plus 3 times square root of 14, plus 3 times square root of 16. So what do we have here? We have the following. Let's see. It's gonna be annoying to do. 3 times square root of 6 is just, we could leave it as that. So eventually gonna multiply by 2. So we could leave it as this. This is gonna be the square root of 4 times square root of 2. So square root of 4 is 2, so it's 6 radical 2. This is 2 and 5, so we could leave this as this. This is 4 and 3, so we're gonna get 6 radical 3. This is 7 and 2, so we keep it the same. And 16 is 4, so 3 times 4 is 12. The nicest one is the last one. Okay, so if you use a calculator to do this, because at this point with radicals you might as well use a calculator, you're gonna get that this is approximately equal to 117.876. So if you use a calculator, that's what you're gonna get that is equal to. Now the most difficult thing is just plugging in and figuring out this formula. Once you have this formula, everything is easy because you just plug it in. You know, you plug it in. I wrote I here. It's supposed to be K because I have a K here. So you just plug it in for K and into the function. Okay, so that's all we're doing. Now, if you were to do this now for the left side, for the left sum, then what we have is the following. We have the sum, again, K equals 1 to 6 of f of xk times delta x. Now, notice that delta x is still the same. It's b minus a over n. So that's not changing. That's still going to be 2. Okay, that's still going to be 2. The only thing that changes now is the xk, because xk now is a plus k minus 1 times delta x, which means that xk is equal, and this by definition that I wrote, which means that this is equal to 4 plus k minus 1 times 2. So it's going to be, we could write 2k minus 2 and then simplify. It's going to be 2k plus 2 if we simplify it. So first I distributed the 2, then I simplified. But now I have my left sum. So writing out the left sum, it's not that difficult anymore because I now have a definition. I just have to apply it. So this is f of 2k plus 2 times 2. That's the sum. And now all you have to do is, again, just plug in into your sum. So again, you could leave, because again, this is a constant, you could leave it on the outside and multiply by all of the heights that are going to follow. So this is f of 2 times 1 plus 2, for the first term, plus f of 2 times 2 plus 2 for the second term, plus f of 2 times 3 plus 2, plus, I'm going to continue in the bottom, plus 2 times 4 plus 2, plus f of 2 times 5 plus 2, plus f of 2 times 6 plus 2. Now, again, this is much easier done on a calculator like on Maple. Maple does all of this work for us. So when you saw in the previous video the 8.8 and the 7.29, it was all of this work being done by Maple. Now we're doing it by hand as human calculators. Anyway, this is 2 times f of 2 times 1 plus 2 is 4. 2 times 2 plus 2 is 6. 2 times 3 plus 2 is 8. 2 times 4 plus 2, that's 10. 2 times 5 plus 2 is 12. And finally, 2 times 6 plus 2 is 14. 2 times 6 is 12, and 2 is 14. Okay? And again, this should make sense, because if you draw it, like, let me just quickly draw it. Again, remember, our left endpoint is 4, and we end at 16. And our width is by 2s. So if you're looking at the last point now should be 14 instead of 16, and the first point should be 4 and not 6. So that should always make sense. If you draw it, you'll always be able to see it and verify your work. But again, we simply now plug in. Again, remember, f of x is equal to 3 radical x. So you plug in 4 for x, 6 for x, 8 for x, and so on. We add it up and multiply by 2, and we get the approximation of the area. So this is 2 times, so this is 3 radical 4 plus 3 times radical 6 plus 3 times radical 8 plus 3 times radical 10 plus 3 times radical 12 plus 3 times radical 14. And much like before, you could try to simplify a little bit. So you have 3 times radical 4 is 6, because the square root of 4 is 2, plus 3 radical 6, plus this is going to be 6 radical 2, plus 3 radical 10, plus 6 radical 2 again, actually radical 3, plus 3 radical 14. And how am I simplifying this? Again, this is an aside. Like, for example, 3 times radical 12 is the same thing as 3 times radical 4 times radical 3, and the square root of 4 is 2, so this is 3 times 2 times radical 3, which is 6 times radical 3. So that's how I get this value here. And again, if you use a calculator, you get that this is approximately equal to 105.876. So now we know that the area of f of x equals to 3 radical x from x equals 4 to x equals 16 is approximately trapped between 105.87 and 117.87. So notice that there's a wide margin of error here, but we do have a value. We do have a value. Okay. Now, for the midpoint, now what changes a little bit is our height, our width. Not with our height, because we're looking at the midpoint now instead of the whole left or right. So again, we have a formula for this, so we use it. So let's see what we get. So using the formula, what do we have? So for the midpoint, again, nothing has changed. We're still going to have the sum from k equals 1 to 6 of f of x k times delta x. Delta x is still b minus a over n, because that's the number of partitions. But now our xk is a plus k minus 1/2 delta x. because we're looking at the midpoint. Okay, so let's see what we get here. So again, our delta x was 2, and we know that our a is 4, so xk is equal to 4 plus k minus 1/2 times 2, which means xk is equal to 4 plus 2 minus 1, because minus 1/2 times 2 is minus 1. And this is the same thing as 2k plus 3. And that is going to be the midpoint. And how do you check that this is the midpoint? Well, remember the first interval? The first interval is between 4 and 6, right? Because the width is 2. What is midway between 4 and 6? 5. Well, since this is our first interval, you plug in 1 for k, and you get 2 times 1 plus 3, which is 5. So this works. This definitely works. Okay, so let's see what we get here. So we have that this is the sum for k equals 1 to 6 of f of 2k plus 3 times 2. And that is equal to the sum, k equals 1 to 6. Actually, that's the sum. So this is equal to 2 times, again, the value. So this is, again, f of 2 times 1 plus 3 plus f of 2 times 2 plus 3. And I'm just going to cut to the chase, plus f of 2 times 6 plus 3. Because we'll see a pattern now. And now, what is this equal to? Well, this is equal to 2 times f of 5 plus f of 7 plus f of 9 plus f of 11 plus f of 13, and the last one, f of 15. Okay, so this is the height of the midpoints, and that's how you get them. Notice that 5 is between 4 and 6, 7 is between 6 and 8, and so on. Like if you didn't know this equation right here, how do you figure this out? Well, for x1, what do? You take one endpoint minus the other, divided by 2, because you're getting the midpoint. So if you didn't know how to do this, you will do something like, okay, what is x1? Well, x1 is the left side plus the right side divided by 2. That's how you get the midpoint. Like for 4 and 6, you'll do 4 plus 6 divided by 2. That's going to be 10 over 2, which is 5. Okay, you take the left side of the interval and the right side, you add them up and you divide by 2, and you get the midpoint. In any case, just to make a long story short, this is 2 times 3 radical 5 plus 2 times 3 radical 7 plus 3 times radical 9 plus 3 times radical 11 plus 3 times radical 13 plus 3 times radical 15. None of these numbers have a square root, so I'm not even going to bother to simplify them. But it's approximately equal to 112.062. So we definitely have a much better approximation for our area than before. So we're getting closer. Now, if you increase the number of partitions, from 6 to let's say 100, then you will definitely come to the solution. Okay? Now, in the next lecture, I'm going to talk about the definite integral and how we obtain it from the Riemann sum. It turns out that the definite integral, it's simply just the limiting process of a Riemann sum. So maybe I should define that. Maybe not. I'll do it in the next time. Thank you for your time.